Right, grade 12s, let's have a look at a graph that we call a cubic function. Okay, a very interesting graph. In fact, it's unlike a parabola that's x squared. This graph has the form ax cubed plus bx squared plus cx plus d. It looks something like that. And what happens is if the a is positive, the graph actually looks something like this. It starts going up to a turning point, comes down, and does this, has another turning point there. And that's what we call a cubic graph. What's very interesting too, it goes from sad and then to happy, and at that moment that it changes, we have what we call a point of inflection. Very, very interesting. A point of inflection where it changes from sad to happy. By the way, this is a turning point here. In fact, this is what we refer to as a local maximum, and this one here is a local minimum turning point. Okay, local means in that region it's a minimum. At that point it's a local maximum. Okay, local maximum, meaning that it's not the maximum, because you can see the graph is going up and up. So this point is not the total maximum, but it is a localized maximum in that region there. And again, the derivative is naught at that point. By the way, if the a is negative, the graph tends to look like that. Okay, and changes from, there's a turning point from happy to sad at the point of inflection there, and we're going to talk a lot about that as we go along. Okay, but let's get into an example where we sketch a cubic graph. If I took, for example, fx is equal to the graph of x cubed, okay, minus 3x squared plus 4, and we've got to sketch this graph. One thing's for sure, I know that little number there is 1, so I know my graph is going to be a very interesting graph. It's going to go something like that. We know that would be its shape. Okay, so it's got 2 turning points and its shape looks like that. Okay, now when we sketch this graph, what we need to do is we need to start off by getting the y-intercepts and the x-intercept. Okay, the y-intercept and the x-intercept. Now, how do we do that? Very simply, we can say for the y-intercept, we're going to let x be equal to 0. So we're going to let x be equal to 0 there. So if you do that, the y would be 0 cubed minus 3 times 0 squared plus 4. And guess what? That's 4. So your y-intercept is 0, 4. Now the x-intercepts, this is where that work on the cubic equation comes in. We let y be equal to 0. And then what happens is you've got a good old cubic equation to solve, like we did in previous lessons. Now, how it works is, remember, you test certain factors of 4. You got plus minus 1, plus minus 2, or plus minus 4, and you've got to find a solution testing those things. Now, if we try, let's say we try x equals negative 1. Let's do that. Let's see if it'll work. Well, negative 1 cubed minus 3 times negative 1 squared plus 4, that will give us negative 1 minus 3, because that's minus 1 squared is 1, plus 4, which is actually 0. So we're going to have one of the x-intercepts will be at negative 1. And that's great, because if that's 0 now, what we can then do is we bring that across. If you remember, just let me write the cubic equation down again. It's x cubed minus 3x squared. Then we've got a 0x and a plus 4 equals 0. And then remember, x plus 1 is a factor. Now remember, if x equals minus 1 works, you just bring that across, and there you've got your factor. And how did we do it? We used the smiley face method. So I'm going to have an x squared here. X times x squared is x cubed. We're missing the middle term, so we write mx, and then 4 divided by 1 is 4. Okay, so that gives us then the last term, and we do the smiley face to connect the x squared terms. So 1x squared plus mx squared is equal to negative 3x squared. We connect the x squared terms, drop the x squareds now, and what do we have? M being equal to negative 4. So we can then, of course, proceed to say, well, x plus 1, x squared minus 4x for m plus 4 is equal to 0. And then we factorize further. That gives us x minus 2, x minus 2. Wow, repeated x-intercepts there. Very interesting. So we've got x is equal to negative 1 or x is equal to 2. Okay, now, Matrix, I want to focus on the turning points of this cubic graph. Okay, it's x cubed minus 3x squared plus 4. And the graph we know, look, it does this. It's going to be this. You're going to see when we draw it, it's going to look like this. There's a maximum there and a minimum there. The gradient is 0 there and the gradient is 0 there. So if we get the derivative of this graph, what is that going to be? Bring down the 3, subtract 1, 3x squared minus 6x here plus 0. At a turning point, the derivative is 0. Okay, so what I then do is divide everybody by 3, and I land up with x squared minus 2x. So then 0 is equal to x into x minus 2, and I've got 2 x values for the turning points, which makes sense. And I think the x will be 0 will be there, so that's where x will be equal to 0 there, and here x will be equal to 2. So I think the minimum is going to be at 2, and the maximum, the local max, will be at 0. But anyway, let's get the y values corresponding to these guys. Okay, let's go f of 0, go back to the original, which is x cubed minus 3 times 0 squared plus 4, and the answer is 4. So your one turning point is at 0 and 4. Okay, then let's look at the f of 2. So it's going to be 2 cubed minus 3 times 2 squared plus 4, which is equal to 8 minus 12 plus 4. And that is actually 0 as well. So there's another turning point at x is 2, y is 0. Okay, now we've got the x-intercept, which we used the method over there of the smiley face, the y-intercept, and we've got its shape, and all we now need to do is to sketch this graph. So let's get a set of axes quickly. There we go, and let's draw this graph. Okay, when we look at this, we've got the, what is the y-intercept will be 4, 0, 4. So let's go and put here 0, 4 is going to be where the x-intercept. So I'm just going to put some markings here, 1, 2, 3, and 4. There's minus 1, minus 2, 1, 2, and so we've got it there. Now, the y-intercept is at 0, 4. So there's a y-intercept there at 0 and 4. Okay, the x-intercepts, let's check them. Minus 1 and 2. Okay, so at minus 1 it cuts there, negative 1, and 2 it's cutting the x-axis. And then it's got a turning point. Well, what are the two turning points? The one is at 0, 4 and 2, 0. And remember, if you're looking at the shape, where its maximum would be at where x is 0. So what actually happens is that it's going to come up this graph like this. It does this, cuts the x-axis at minus 1. Okay, goes up like this, turns and cuts the y-axis there. And it's going to come down, and it's going to do this. There it comes down, and it goes like this, and it turns at 2 and cuts the x-axis. So there it is. It's cutting at 2. That's your one turning point. There's your other one, and that's your other x-intercept there. In fact, that could be minus 1 and 0. Okay, now, what is very interesting, you'll notice that this is the local maximum and the local minimum. Once you know how to get the turning points and you know the shape based on, remember it's 1x cubed, that is positive, okay, minus 3x squared plus 4. This is the y-intercept, but the turning points are at 0, 4, and 2, 0. Okay, now there's one other thing that we need to focus on where it changes from sad to happy. And what we do, now don't worry about this, is there's a principle which is quite a complicated thing. We've already got the derivative, which was 3x squared minus 6x. Now if you differentiate again, you're going to get 6x minus 6. And if you put the second derivative equal to naught, you then get what we call the point of inflection, and that's going to happen at x equals 1. What is the corresponding y value there? Well, the f of 1, go back to the original, is 1 cubed minus, let's just tidy that up a bit, minus, so there's 1 there, let's go there, minus 3 times 1 squared plus 4, and that equals 1 minus 3 is negative 2 plus 4 is 2. There's a point of inflection at 1, 2. Now let me explain that. At 1, 2, so at 1 and 2, we've got what we call a point of inflection, an inflection point, where the graph changes its shape from sad to happy. By the way, there is a much easier way of doing this. You don't have to get the second derivative and put it equal to naught. That's, to me, a little bit complicated. Let me show you a brilliant way of getting the point of inflection. If you add up the x values of the turning points, so in other words, you add up the x values of the turning points, and then you divide by 2. Now watch this. The x values of the turning points would be 0 plus the x value of the other one is 2 divided by 2, and 2 over 2 is 1, and you get your x as 1. So I would say get the x values of the turning points, add them up, divide by 2, and you'll have your point of inflection where the graph changes from sad to happy. Or just simply use the second derivative test here, where you you've got fx, you differentiated it, and you do the second derivative on this thing, put it equal to naught, and there you go, and you've got 1, 2. But I like this idea of taking, it makes sense because the point of inflection happens between the two x values of the turning points there.